we're going to need, of course, quantum channels, these photonic, optical fibers to connect the logical QPU units. And of course, as I mentioned before, there's all the classical networking we need to communicate the measurement results, but also instructions, schedules, and different classical signals that we need to coordinate. So we have the quantum and classical network stack in the middle here in that diagram, but I did want to quickly dive into what is a logical QPU, this LQPU. So we spoke about the physical QPUs before, superconducting, trapped ions, etc. But to make it a logical system that can really go beyond the noisy regime, where these become very useful in a quantum data center setting, is all the subsystems around that physical QPU. So we need a real-time host. This is a CPU and perhaps some GPUs that can be very fast at carrying out some of the critical steps in error correction. So for decoding the syndrome data that we're getting from our ancilla qubits, for conducting some logical orchestration of the single QPU itself. So how to orchestrate these physical qubits and logical qubits and the error correction versus computation dance and orchestrating all of that. That can be carried out by this real-time host. And then one level lower than that, we have the quantum system controller. So this is responsible for, again, driving those physical qubits, carrying out the native instructions that the physical QPU platform can actually understand. So it's generating pulses or controlling certain laser systems to really drive these physical qubits. Oftentimes, these controllers are implemented with a combination of CPUs, FPGAs, RF system on chip, different platforms depending on the QPU we're talking about, but it plays the same kind of logical function. But we need all of these three layers to turn that physical QPU platform into a logical QPU that can carry out some reliable quantum computation.